The final process we are going to talk about this week is the Poisson process. And obviously, as the name suggests, it is related to the Poisson distribution, but we will see how. First, let's define the Poisson process. Consider events occurring at random instants of time at an average rate of lambda per second. Now, we also had started with a similar statement when we described the Poisson distribution, but there we had a constant time interval, okay? And the expected value of events in that interval was lambda. It was not a rate or lambda per second, it was just plain average, okay? But here we have the time component. Here we have, again, random events, okay, occurring at a random instance. But now we know the average rate. So that means the average number of events per time unit. Well, I have specified it to be a second, but it doesn't really matter. You just have to have a rate lambda per time unit. Now we will define the random process n of t as the number of events in the interval 0 up to t. So essentially you are, as the time rolls on, you are counting the number of events. Here is a sample run of this process. You see, this is the first occurrence here. So up to this point, the random process n of t is 0. At this point, you have a jump. It becomes 1, okay? And up to this point, which is the arrival of the second event, it stays at 1. And at this point, it jumps to 2 and stays there until this point, which is the arrival of the third event, at which point n of t becomes 3. And so on. It goes on like this. And we call this one, this one, this one, this, and so on. We call this inter-occurrence times or inter-arrival times. Okay, this is a very prolific terminology, inter-arrival times, especially in the study of queues. If you look at the properties of the random process n of t, it's first of all non-negative, obvious because you are counting. So the count cannot be negative. It's integer valued, again, with the same reason. It's non-decreasing, right? Because you are counting upwards. And it's continuous time. Okay, you are observing the entire timeline. It's a continuous time random process, and it starts from 0. At time equals 0, you start from 0. So such processes we call counting processes in general. Okay, so Poisson process is a special case of counting processes. Binomial counting process is also another counting process. It's not continuous time, it's discrete time, but it still has these other properties. It's not negative, it's integer valued, it's non-decreasing, and it starts from 0, so it's a counting process. Poisson process is also a counting process. Now, we are going to derive the distribution of the Poisson process as we did the Poisson distribution, and we will study its mean and autocorrelation. And also, later on, we will derive the inter-arrival time distribution, okay? So what we do is going to be more or less the same with what we did with the Poisson random variable. We'll just divide the interval 0t into n subintervals of very short duration. Delta equals t over n. N will go to infinity, so delta will go to 0. And we will assume the following. More than one event in a subinterval is negligible. So it's either 0 events or 1 event, exactly 1 event. And event occurrence in one subinterval is independent of all others. Okay, so every time instant is independent of other time instants, whether an arrival or an event occurs or not. That's independent for all time instants. So the result of these assumptions, each subinterval we can model as a Bernoulli trial, obviously. Either 0 events or 1 event. And also occurrence of an event in each subinterval constitutes an IID Bernoulli sequence because we have assumed every instant is independent, and the probability of event occurring in a subinterval is the same for all intervals, it's uniform, then we have an IID Bernoulli sequence. Therefore, the Poisson process will become the limiting case of the binomial counting process. So as you see, it's very parallel to the Poisson distribution. If you remember, the Poisson random variable was the limiting case of a binomial distribution where n goes to infinity, p goes to 0, but n times p was constant and lambda. Here it will be a little bit different because we have the time component. N times p will be equal to not lambda, but lambda times t, because now lambda has a different meaning. It's not the expected number of events in the interval, it's the expected number of events in a unit interval. So in time 0 to t, the expected number of events is not lambda, but lambda times t. In this case, again, we are going to take delta, which is equal to t over n, to 0, n to infinity, and obviously p to 0, but this will be fixed. Okay, lambda times t is going to be fixed for a given t. So in this case, the number of events in the interval 0 to t will again be the limiting case of a binomial distribution, which turns out to be obviously a Poisson distribution, but with parameter lambda times t. Okay, so essentially the number of events at time t of a Poisson process is essentially a Poisson random variable with parameter lambda times t. Okay, that's the relationship between the Poisson process and the Poisson random variable. This is the same distribution, but with the parameter lambda times t. And therefore, since we have the distribution, we can now write the expectation and the variance quite easily. The expected value is lambda times t, because if you remember, the expected value and also the variance is equal to the parameter for a Poisson distribution. So it's lambda t in this case. So the expectation is equal to lambda t, and the variance is also equal to lambda t. Therefore, we see that the mean itself is dependent on time, which makes perfect sense because you are counting the number of events, and if you shift the time origin, obviously you are either keeping some events out from your original count, or you will have to include some other events if you shift towards left. That means the expected value of events being dependent on time is not unreasonable. So the Poisson process is not stationary in any sense. It has dependence on time in distribution also. And let's look at the autocovariance or autocorrelation functions.